Hi, my name is Lee Brinson. I'm an electrical engineering instructor at Salt Lake Community College. In this next video, we're going to, actually going to turn our attention now to analyzing circuits that are driven by sinusoidally varying, or AC, sources. This is what we're going to refer to as the sinusoidal steady state. By this, we're going to assume that the system has been operating, that the sinusoidally varying sources have been applied long enough that any transients that might have occurred at startup have all died out, and we're now operating in the sinusoidal steady state. To do this, and to analyze these kinds of circuits, we're going to use something known as phasors. So to begin with, we're going to introduce this concept of a phasor. A phasor is a complex exponential way of representing trigonometric functions. We'll then turn our attention to and define what we mean by a complex impedance. We'll then analyze or demonstrate ways of analyzing these RLC circuits, resistors, inductors, capacitors, or circuits that have resistors, inductors, and capacitors in them in the sinusoidal steady state, including looking at series connections and voltage division, parallel connections and current division. We'll see how node and mesh analysis applies in the sinusoidal steady state involving phasors and impedances. And then we'll look at, again, Thevenin equivalency and maximum power transfer concepts in this sinusoidal steady state. So here we are again in the complex plane, where we have a real axis and an imaginary axis. And we know that we can represent points in this plane. Now, we're going to be using a complex number to represent a voltage. So let's now just start out with a complex number. We'll call it V, and say that it has a length, which we'll call V sub m, and it has some angle theta. So there's theta. Again, the length of this is V sub m. So it's a complex number. The magnitude of the complex number is V sub m, and the angle associated with it is theta. Of course, that represents the polar representation of this complex number V. We know that another way of writing that is to say V sub m e to the j theta. And we also know that we can express it using Euler's formula, or simply pointing out that the projection of this point onto the real axis is equal to V sub m times the cosine of theta. So we can write this as V sub m times the cosine of theta, gives us the real part, and the imaginary part is just V sub m times the sine of theta, or this can be rewritten as V sub m times cosine of theta plus j sine of theta. And just a little bit of nomenclature here. We can say then that the real part of V is equal to V sub m cosine of theta, and the imaginary part of V is equal to V sub m sine of theta. Alrighty, here's where it starts to get interesting. Up until now, theta has been a constant value. What if we start allowing theta to be some function of time? And in fact, let's begin with by letting theta of t equal some constant omega times t. Omega is going to have the units of radians per second, so that when we have radians per second times seconds, that gives us radians, or a measure of an angle. So sure enough, theta is an angle, or has the units of radians, or equivalently degrees. By the way, omega is referred to as the radial frequency term. So now let's rewrite our V. V then is equal to V sub m e to the theta, but theta is equal to omega t, so it'll be e to the j theta, or e to the j omega t, which, again, using Euler's formula, can be written as V sub m times the cosine of omega t plus j sine of omega t. Given that the real part of V is the projection of this point down onto the real axis, and given now that theta is starting at t equals 0, theta equals 0, and as t increases, we now see that theta is increasing linearly as a function of time, which means that the real part of this complex number, as theta increases with time, the real part of it, which is the projection onto the real axis, is going to be changing as a function of time also. The real part of this now becomes a function of time, and if we stop and think about it, we know that the projection onto the real axis is just the magnitude v sub m times the cosine of this angle, the angle being omega t. We have then that the real part of v, writing it, the real part of v then is equal to v sub m cosine of omega t. And hopefully now you'll start to see where we're headed with this. This v sub m cosine omega t is the way of numerically or mathematically representing a waveform that's oscillating cosinusoidally at a frequency of omega t seconds. We can see graphically what's happening. Let's now overlay a time domain axis coming down like this, and let's plot as a function of time the projection onto the real axis of this point as it goes around at omega radians per second. Just draw a couple of lines down here to help me graph this. So at t equals 0, theta equals 0, the cosine of 0 is 1, and we start it here at a maximum. Now we allow theta to increase, and as we do so, the projection on the real axis decreases until we get to theta equaling pi halves, or 90 degrees, at which time the real projection equals 0. Continuing on through theta until theta gets around here to pi, or 180 degrees. Once again, we have a minimum here. It comes back, crosses, as theta gets down here to 270 degrees, and back to where we started. As theta goes around and around, this graph then continues on and on, and you'll see, hopefully you recognize then, that what we have here is a plot of the function v sub m cosine of omega t. Now this analysis assumed that theta started at 0 radians per second. Let's now take a look at what happens if we start our angle at not 0, but at some angle phi. In other words, theta at t equals 0 equals phi. Now when we start this projection coming down here, or first of all, we then would say that theta as a function of time then is equal to omega t plus phi. And our complex expression v is equal to then v sub m e to the j theta, but theta is now omega t plus phi, which, again, using Euler's formula, we can write as v sub m times the cosine of omega t plus, cosine of omega t plus phi plus j sine of omega t plus phi. And we can say then that the real part of v is equal to v sub m cosine of omega t plus phi. A completely arbitrary cosine term, specified by its amplitude, v sub m, the rate at which it's oscillating, omega, and this arbitrary term, or arbitrary offset of phi radians. Let's plot that projection onto our time domain as we did before. Only now, instead of starting at t equals 0 with theta equaling 0, we start at t equals 0 at phi. And again, dropping these down to just help me draw this. We're starting here at this point. It goes to 0 when theta gets to 0, or to 90 degrees. By the time theta is around here to pi, we're down here to minus, or the negative, coming back this way. And once again, we have a cosine waveform, but it's a cosine waveform with a phi degree or phi radian shift. Let's take this term and rewrite it using properties of exponents to take our analysis just another step further. Thus we can say then that v is equal to v sub m e to the j omega t times e to the j phi. Just the multiplicative property of exponents. Now let's rewrite this as v sub m e to the j phi times e to the j omega t. As we do that, we see that this term here is the time-dependent term, and it varies as omega t. But we also see that we have these two terms here which are constants. In fact, we have a v sub m e to the j phi. We have another complex number involving the amplitude of our cosine wave and this arbitrary phase shift. It turns out in RLC circuits, linear circuits in general, that are driven by sinusoidally varying waveforms, that the frequency omega doesn't change. In other words, every current and voltage in a circuit thus driven will be oscillating at the same frequency. The only thing that changes, the only differences between various currents and voltages within this waveform are the amplitude and the phase of those currents and voltages. This term here is so important, we give it where we create a new complex number called Phasor v. And Phasor v then is simply equal to this v sub m e to the j phi. V sub m e to the j phi. I'll say it one final time. Phasor v is a complex number. Its magnitude, v sub m, is the amplitude of the cosine wave that we're wanting to represent in terms of a complex exponential, and its angle phi is the arbitrary offset or the phase shift of that function. Let's just look graphically at what we're talking about then. Here is a cosine waveform that goes through its maximum at t equals 0. In other words, it has no phase shift. We would write then the phasor representation of this would be v sub m e to the j 0. Well, e to the 0 is 1, so this is simply equal to v sub m. For a waveform that's got some finite shift to it, we would write it, phasor v, then is equal to v sub m e to the j phi. So this thing right here, this complex exponential term, is going to represent a waveform, in this case, that is shifted phi degrees away from the original or the non-shifted waveform. This blue one is cosine omega t. The red one is cosine omega t plus phi. In this case, phi is a positive 90 degrees. Alrighty, let's just close up here by giving 3 examples. Here we have the time domain representations. And over here, let's go ahead and write the phasor transform, or the complex exponential way of representing these trigonometric functions. So on this first one, phasor v1 would be equal to 5e to the j0. But again, e to the 0 is 1, so that would simply be 5. Phasor v2 would equal 4e to the j60. And phasor v3 would equal 3e to the j minus 90. We typically put the minus sign out here in front. E to the minus j 90 degrees. I have represented here the time domain functions v1, v2, and v3. v1 is the blue one. It goes through a maximum at t equals 0 and has an amplitude of 5. Amplitude of 5, no phase shift. The blue one is v2. It has an that was the blue one we just talked about. The green one has an amplitude of 4 volts, and it has a phase shift of plus 60 degrees. So it's been shifted to the left by 60 degrees. I mean, under these circumstances, we would say that the green one, because it peaks out before the blue one does, we'd say that the green function, v2, leads the blue function, in this case by 60 degrees. Finally, the red function shown here corresponds to V3. It has an amplitude of 3 volts, and it is shifted to the right 90 degrees. So the red one lags V1 by 90 degrees. All three of these are oscillating at the same frequency. Omega is the same for all three of them. They differ only in amplitude and in phase shift. We're going to use these complex exponentials instead of trigonometric functions as we analyze these RLC circuits, because it's a whole lot easier to do exponential mathematics than it is trigonometry with all of its identities and complicating trigonometric properties.